Hello friends, welcome back to the third quarter of complex numbers. In this quarter, we are going to learn topology in the complex plane, and topology is the subject of study of shapes. Herein, we are going to learn sets in complex plane, interior points and boundary points, open and closed set, closure and interior of a set, connectedness, connectedness for the complex set C, bounded set, and the point at infinity. Now consider circles and disks. Let us consider a circle of radius r, and the center of the circle is z0, which is having coordinates x0 and y0. Now we are talking about the disk, and BR, which is function of z0 because it is centered around z0, is set of all complex numbers z that belongs to the set of complex numbers C with double bar, and z has a distance less than r from z0. Now the disk is of radius r, which is centered at z0. Let us suppose that this is the disk and this is the center z0, and let us suppose that this is a real axis which is representing the numbers x, and this is imaginary axis that is representing the numbers y, and we are interested in all those complex numbers z that has distance less than r from z0. So obviously here we are talking about all points inside the circle that forms a disk. So this is that disk. Now k of r z0 represents complex numbers z from the set of complex numbers we are in general writing C with double bar, as z has distance r from z0. So here strictly we are talking about all those points which are at distance r from the center. So here we are talking about the circle of radius r centered at z0. Now there is a small question how we measure the distance. And when we are interested in measuring a distance, what is the methodology that we follow? Now let us suppose that this is a real axis and the vertical axis is an imaginary axis, and I am talking about a point z0 here, and that has expression z0 is equal to x0 plus I times y0. So obviously this distance on real axis is x0, and the same point has y coordinate that is falling normally on imaginary axis can be represented by y0. Now we are talking about another point z that has coordinates x and y. I am calling this as an ordered pair of z because here I can write z is equal to x plus iy in the similar fashion. Now this point z is at some distance from z0, and we are interested in measuring that distance. Now this point has coordinates. One coordinate is x and the another coordinate in the same fashion we can write as y. Now I am interested in the distance between this point and this point. Now obviously this distance is x minus x0. So this distance is x minus x0. Similarly, this vertical distance is y minus y0. This is the coordinate y and this is y0. The difference is y minus y0. Now obviously in this right angled triangle, the distance between 2 points which are at which is the hypotenuse of the triangle, we can write this distance to be d, and that d is equal to under root of x minus x0 square, x minus x0 square plus y minus y0 square. So this is the Pythagoras theorem we are exploring at this point, and we can find the distance between 2 points. Now that here we have written d as a distance under root of x minus x0 whole square plus y minus y0 whole square, this can be written as mod of x minus x0 plus I times y minus y0. So this is mod of z minus z0. So the point is that mod of z minus z0 represents the distance between 2 points. So Br of z0 represents set of all complex numbers z that obey the condition mod of z minus z0 is less than r. So this is the condition of the disk, and Kr set of 0 represents set of all complex numbers that obey the condition mod of z minus z0 equal to r, that it represents the boundary of the circle, boundary of the disk, and here this quantity BRZ0, this is talking about the disk except the boundary points. Let E is subset of a complex number and a point Z0 is interior of E if there is some R greater than 0 such that boundary of that number Z0 is subset of E. Let us suppose that we have some region of space which forms a subset of a complex number. So the general complex set is C double bar and E is this selected region. Let us imagine that this portion is out of E, is not included in the region E. Now let us imagine a point and let us call this point as Z0. Now Z0 is an interior of E if there is some r greater than 0 such that Br of Z0 is subset of E. So here we consider a small disk of radius r around Z0, and if this disk is included into the region E, then that is called as an interior point. Now let us imagine that we have a point here. Whether it is interior or not, we shall develop a disk of radius r where r is non-zero and some portion is included and some is not included. So this is boundary point by definition. So the boundary point B of E, if every disk around B contains a point in E and a point not in E, just we have seen now, and such a boundary set is technically denoted by del E is set of all boundary points for region E. Now we are in position to discuss open and closed set. Let U represents a set which is subset of complex numbers, which in general is denoted by C double bar, is open if every one of its points is an interior point, then it is called as open set. A set A, which is subset of complex number C double bar, is said to be closed if it contains all its boundary points. Now with examples, we shall try to understand openness and closeness of a set. Let z belongs to the set of complex numbers and mod of z minus z0 is less than r, and z belongs to set of complex numbers such that mod of z minus z0 is greater than r, r open. Here we have considered the points which are inside the circle of radius r and outside the circle of radius r, except the points which are on the circle of radius r. So they are called as open. This set is called as open because it contains every one of its point as an interior point. Nothing on the boundary is considered. A complete set of complex numbers C with double bar is called as open set because there is no boundary. This is a very technical thing. Similarly, the empty set which does not contain anything is technically referred as open set. Consider Z belongs to a set of complex numbers such that mod of Z minus Z0 is less than or equal to R. So here we are considering all points on the circle and inside the circle, and we are adding to that set of numbers Z that belongs to set of complex numbers such that mod of Z minus Z0 is equal to R. They are known as closed set. So here we have included the condition here, and all the points having red color here, they are forming a closed set. Consider a set of complex numbers C, which we have already considered earlier. So here we can consider this set as closed set as it contains all of its boundary point. Here we have considered openness of it. We can also consider closeness of it. That is technically valid, and same is valid for empty set. Now let us consider the last example. Z belongs to the set of complex numbers such that mod of z minus z0 is less than or equal to r. So we are talking about only red color dot points as a first part, and that has forming a union with another condition wherein z is set of all those complex numbers such that mod of z minus z0 is equal to r if and only if imaginary of z minus z0 is greater than 0. So here we are considering all points which are above this line. So here this set is neither open nor closed. So we are again at the definition of closure and interior of the set. Let E is a set in complex numbers. The closure of E is the set E together with all boundary points represented by E bar, which is union of E and del E. The interior of E is written as E0 on its top, is a set of all interior points. So by this definition, closure of E, which we write as E bar, that is equal to E union del E, that is interior of E union with boundary of E. This we can write as BRZ0 bar, which is closure of BR at Z0, that is equal to BRZ0, that is interior points of Z0 union boundary points of Z0. So that is equal to set of all complex numbers such that mod of Z minus Z0 is less than or equal to R. Now that KR represents a circle of radius R which is centered around a point Z0. So this is a circle of radius R. The point at the center is again Z0, radius of the circle is r, and this is prevailing in the complex plane wherein x-axis we are calling as real axis and y-axis we are calling as imaginary axis. Now kr, as I said, represents a circle of radius r, and closure of that will represent all interior points along with the boundary points. Therefore, closure of kr is nothing but the kr. Now br is a disk of radius r, and this is centered around a point z0. Now here we propose that we are excluding the center z0 from this consideration, and after doing so, when we consider closure of this, then we are again including z0. That is what it is. So this is equal to z belonging to the set of complex numbers such that mod of z minus z0 less than or equal to r. So that center which we have excluded here, that we have again considered back by considering the closure. So here in fact we are trying to learn the game of notations in this closure and interior of a set. Now let us suppose that we have a set E such that it is containing complex numbers Z which are belonging to the set of general complex numbers C W bar such that mod of Z minus Z0 is less than or equal to R. So in fact what we are doing, we are considering a disk of radius R, and we are considering the boundary of the disk together with the interior. Now, when we are writing interior of E and denoting as E0, then it is BRZ0. We are throwing away the boundary points and we are considering the interior of the disk. Now, the next argument is that a set E contains all points on the circle of radius r which are centered around z0. So here we are considering the boundary of a circle of radius r which is centered around a point z0. Now only red points here are under consideration as set E. Then interior of that is nothing. So that is a very technical kind of thing. So interior of that is empty set. Now we are in position to discuss connectedness. A set is connected if it is in one piece. For example, if we consider some region and designate that it is a set A, this is having complete connectedness. But we shall try to understand this definition more precisely. Let us suppose that we have two sets x and y in complex numbers. They are separated if there are disjoint open set u and v. Disjoint means there is nothing common. Let us suppose that u and v are disjoint. It means that the common of u and v is an empty set. There is nothing common in u. Now x belongs to u and y belongs to v. A set W in C is connected if it is impossible to find two separated non-empty sets whose union is W. We shall try and understand this definition with an example. Therefore, this point 1 is a point of disjoint, and that makes set X and Y having nothing common. So intersection of X and Y is definitely an empty set that contains no point. So we are following the definition. So this is a disjoint at 1, and there's nothing common in between 2. And now we are considering U as B10. Earlier we were considering that BR as a disk of radius R centered around a point Z0. Now here B10, it means that it is a circle of radius 1. So this is origin, this is a point having coordinate 1, this is 2. Now here we are considering a circle of a radius r, that is r equal to 1, centered around a point origin. So this is the circle under consideration. And V is BRZ0. Now R again is radius is 1 and that is centered around point 2. So therefore the second circle appearing here is represented by V. So here when we consider X union Y, it is 0 to 2 excluding 1. So the common point to the two circles is the only one point, and that point is having coordinate x equal to 1. And we have excluded it from definition. So there is nothing common between U and V. And when there is nothing common between the two disjoint sets, open sets, then it is impossible to, that has some union which is equal to W, and W is not empty. So it is impossible to have W not empty, because here the common intersection is an empty set. Now from this example it is very clear that these two sets are not connected, but other way around is difficult. It is hard to check whether a set is connected or not. For open sets, there is much easier criterion to check whether or not a set is connected. We are going to understand through a theorem this thing, and we are not going to prove this theorem at this point in time. Let G be an open set in complex. Then G is connected if and only if two regions in G can be joined in G by a successive line segments. This is a very simple argument. That is, let us suppose that we have some object which is of having a random shape and that makes a complete contour. Now inside this region, let us suppose that there is some cavity, some hole in between which is not part of the set. Here let us suppose that this is the region which is not a part of the set. Now we are considering 2 points. Let us suppose that the 2 points are under consideration like this, A and B. They are part of the set, say E. Now the set is said to be continuous if we can draw a line from A up to B and that line is included in the set, then the set is said to be connected. Now we are in position to discuss boundedness. Let A is in complex plane is bounded if there exists a number r greater than 0 such that A contains BR0. Let us try and understand this. Let us suppose that we have a complex plane under consideration, and in this complex plane we consider some region of space which is a set A and that is in the complex plane. Here we can consider a circle of radius r around origin such that this entity is completely bounded inside the circle. At the same time, we consider some region Let us suppose that we have two lines having angular variation like this. So this set is unbounded. Now we cannot have a finite circle of radius r that will include this green region. So this set you can call unbounded, and this red one you can call bounded. In real set, there are two different directions that gives rise to a way to infinity. For example, we consider this line. Let us suppose that this is 0. So here one can go on traveling in the right hand side direction and can approach to infinity, which I am going to call plus infinity. Similarly, one can travel on negative direction such that we can reach up to the entity minus infinity. So here there are two directions that gives rise to plus or minus infinity. Unlike the quantity in real sets, we have only one infinity in the complex plane. Now let us suppose that this is a complex plane and this green arrow is representing real axis and the red one is representing imaginary axis. So here we can go towards infinity, 1, 2, 3 and so on, we can reach up to infinity. So here minus 1, minus 2, minus 3, we can again reach up to infinity. Then we can go in the direction 1i, 2i, 3i and so on, we can reach here to infinity. Similarly, in the opposite direction, we can go to reach up to infinity. Now, here we are going in a different way. 1, then we are going to 2i, then minus 3, then minus 4i, and then 5, and then so this is the way we are having a spiral direction of going towards infinity. Or one can travel in this direction for infinity, which is passing from 1, 1i. You can randomly choose different directions. So there are many directions in which we can attain infinity.